So now let's look at how delta G is related to some of the other constants that we have talked about in this class. So one of the main ones was equilibrium constants K, and we're going to see how delta G and K are related to each other. So we're going to take some of the concepts that we understand with equilibria and see how they compare to what we've just learned with delta G. So there's a relationship between delta G and Kp. This is the equation, and so the idea is that they are directly related to each other. So delta G is equal to negative RT times the natural log of Kp. R is our gas law constant in joules per mole Kelvin. Temperature is always going to be in Kelvin. And remember, Kp is our equilibrium constant in ATM. So one of the main tricky features here is that because we are using R, the units on energy are going to be in joules. So the delta G that we get out or use in this equation has to be in joules per mole. So that's kind of the tricky point here. So the units on delta G must be joules per mole because the unit of energy inside of R is joules. So before we can actually do these calculations, this kind of makes sense that using this equation, when we have a negative delta G, we are going to have a very large Kp. And so that makes sense. So a negative delta G means a spontaneous reaction. A large Kp means that the products are highly favored over the reactants. So there's much more products than reactants. And so that's how these two constants kind of play together. A negative delta G, a spontaneous process means that the reaction is going to go very far to the right, which means we're going to have more products than reactants. We're going to have a large Kp. So the exact opposite is true. If I have a positive delta G, a non-spontaneous process, it means the reaction's not going to go forward very far. So we tend to get a small Kp. So that means that the reactants are favored over the products. So a non-spontaneous delta G or a positive delta G means that the reaction's not going to move forward very much. The products are very small compared to the reactants. So here you can actually do some calculations. I give you a reaction. The reaction really doesn't matter very much. I need to give you delta G, and in this case I want to find Kp for a given reaction at 25 degrees C. So I'm going to use my equation that relates these two. So remember, even though I'm given delta G in kilojoules per mole, I've got to convert it to joules per mole. So if in case you haven't seen this trick, to go from kilojoules to joules, you just multiply by 10 to the third. So I need to make that conversion. R is a constant that is typically given. The other thing I need to do is convert my temperature into Kelvin. And from there, it's just a little bit of algebra. So if I solve for Kp, I get Kp is 5.85 times 10 to the fifth. So that makes sense. If I have a negative delta G, I would expect Kp to be a fairly large number. And so 5.85 times 10 to the fifth is actually quite a large number. And then remember, equilibrium constants do not have units.